Hello and welcome to my YouTube channel. This is Ramani Online Mathematics. If you know you have not subscribed, please subscribe, share to your colleagues. Today we are going to look at heat equation. We are continuing with it. Solve the heat through heat. Solve heat conduction equation. UTT equals 17UXX. So let me write it here. Solution. UT equals 17UXX. And the interval, this is the boundary condition at 0 to pi, is also given to us. U to 0, U of 0 t equals U of pi t equals 0. T is greater than 0. And the initial condition has been given to you here. Okay. So let's start with it. So the first thing we said that you have to set your own solution. This is your own solution. Your own solution should be in terms of x and t, which will give you x of x, t of t. Is that okay? Then the next thing to do is that we are going to put the boundary condition to set our boundary conditions. So here, the meaning of this is that either u of 0t equals 0 or u of pi t equals 0. So when it comes to here, if I put it, I'm going to have x of 0, t of t is equals to 0. Because when you put 0 here, this place means that x is 0. So if you put 0 here, t is t, then the u is equals to 0. So here I'm going to have x equals 0, but I said that t, the time function should be greater than 0. So it's never going to be equals to 0. The same thing should apply to the pi. X of pi, t of t should be equals to 0. It means that x of pi is equals to 0. T of t is never equals to 0. Is that okay? It's like when you solve quadratic equation, you get an answer. Either one of them goes to 0. So either this or that. But you know that time function cannot go to 0. So it's the pi one that can go to 0. That's why you are putting it there. So we're done with that one. Now that we have set our boundary conditions, so let me write the boundary conditions somewhere. So this is going to be our boundary conditions. X at 0 equals 0. X at pi equals 0. So these are our boundary conditions. We are going to use this throughout the week. Very good. So now that we have this, you see the first example we solve, I've named it heat equation part 1, P1. You could see that one. The thermal conductivity was just 1. That's why I didn't even write. You see there was nothing here. But here, the thermal conductivity here, which is alpha squared, is 17. Is that okay? Okay, so now that we have this, let's take our function, which is u equals xt. Let's differentiate with respect to t. So we're going to have ut equals xt prime. Is that okay? Then also differentiate it with respect to x. That will give you x prime prime t. Is that okay? So we are just coming back to this place and you substitute this into this. Is that okay? So when I come here, my ut is xt prime. Let me write it here. Xt prime is equals to 17 uxx is x prime prime t. X prime prime t. Is that okay? So here, this is what we have. So let's divide it. Let me write it twice so that you can see what it's x t prime equals 17 x prime prime t. So let me divide here by t prime over 17t equals x prime prime over x. You can only decide that you bring the 17 here. Wherever you bring it, no problem with that. Is that okay? And we say that all this should be equal to what? Lambda. It means that if I take t prime over 17 t should give me lambda, which will give me t prime equals lambda 17t. So t prime minus lambda 17t equals 0. Is that okay? Now the other side we have x prime prime equals lambda x prime prime minus lambda x equals 0. So these are the two solutions we have so far. We are going to deal with this. But remember when we were solving, I said that because here the xx, you see the boundary condition has been set. So we are going to deal with this one first. And this one goes with three cases. Case 1, case 2, case 3. So the case 1 is that when lambda is what? Equals to 0. Case 2 is when lambda is greater than 0. Case 3 is when lambda is less than 0. You set all these cases. Then you check the one that gives you non-trivial solution. You use that one. So let's start with case 1. So when lambda equals 0, what do you get? So you come back here. Patch your debut. You come back here. Then you substitute wherever you see lambda, you put 0 there. So when I do that, I'll have x prime prime equals 0. Because if I put 0 here, everything will go to 0. 0 times the function x will be 0. So here, we need to what? Integrate. So let's do that. X prime prime is equals to the integral of 0 dx. Remember, we are integrating with respect to x. So here will be x prime equals a. You know, the a is what? Constant. If you integrate 0, you get 0 plus the constants, which is I'm using a to represent that. I will integrate it again with respect to x again. And when you do that, you have x of x. So if I integrate this, let with only function of x equals to, this will give you what? Ax plus another constant. Let's use b. Is that okay? Now, there was a condition that was set here. This is a condition. X of 0, x of pi. Now, for the x of 0, let's use when small x equals 0. Then capital X will also be equals to, you know, this capital X is this. And then this 0 here is a small x. So when you do that, wherever I see capital X, I'll put 0 there equals a multiplied by 0 plus b. This tells you that my b is what? 0. Is that okay? And if b is 0, you then move to this side. Here too, capital X is 0, but small x is pi. So when I substitute here, capital X is 0 because small x is pi, so I have a pi. Already b, we had 0, so we don't need to bring it. If I divide both sides by pi, I will see that I have my a to be 0. So since a is 0, b is 0, we say that this yield trivial solution. I've told you that trivial solution means that all the solution you had is 0. Is that okay? This yield trivial solution. So you can't conclude, you have to move to the next case where when lambda is greater than what? 0. Is that okay? So now case 2, when lambda is greater than 0, we said that let lambda to be equals to p squared. Is that okay? Lambda should be equals to p squared. Why are we saying that? Say that lambda is greater than 0, so we only need positive numbers. So even where p belongs to r, okay? Where p belongs to r, the reason is that, so even when you put positive and negative number here, once you square it, becomes positive. So that's why I said lambda should be equals to p squared. So when I write the equation, where we have x prime prime minus lambda x should be equals to 0. Wherever you see lambda, I put p squared there. So I'm going to have x prime prime minus p squared x equals 0. This, when it comes to OD, this is second order. So you want to solve this, and you know that day I explained it. So this place will be r squared equals 0. That day when I was explaining, I said that this one is order 1, it's not order 1, this is order 0. If it is order 1, you see the prime there. Okay, this is order 0. Now, r squared minus p squared equals 0. So you're going to have r squared equals p squared. You will take square root on both sides. Remember, you bring your plus or minus. So my r will be plus or minus p. So this is the solution. This is a distinct root. Distinct root. So when you get distinct root, this is how you write a general solution for it. You know, this is in terms of x. So x, you see, we are looking for this, will be equals to so we bring the constant for which is e p x plus b e p negative p x. Okay, so this becomes your solution. So you are now going to substitute and see whether you get 0 or you will not get 0 for a and b. Is that okay? So now looking at our boundary condition, if x is 0, capital X is 0, small x is 0. So here, if I put 0 here, you see that it will be e to the power 0. Everything here go to 1. Here it will be e to the power 0. Everything here goes to 1. So it will leave with a plus b equals capital X is 0. So equals 0. Is that okay? So here you can say that b is equals to negative a, or a is equals to negative b. Good. Now, after getting this, let's come back here and do the other one. When small x is pi and capital X is 0, so we are going to have 0 equals a e p pi plus b e negative p pi. So my 0 will be equals to, you see this b is the same as negative a, so I can write this one as a e to the power p pi minus, instead of a, sorry, b I represented by negative a, e negative p pi. Now the a are common, so I can write 0 equals a bracket open e to the power p pi minus e to the power negative p pi. Good. Now here, either a is equals to 0 or this is equals to 0. But you and I knows that there's no way that exponential function can go to 0. Even e to the power 0 is 1. So therefore, a is rather equals to 0, and e to the power p pi minus e to the power negative p pi can never be equals to 0. So this is what you will get. Now, after getting this one too, a is 0, so we have to get b. So my b will be equals to 0 because b is equals to negative a, which is the same as 0. Now let's move to the last case where it said that lambda is less than 0. So that we let lambda to equals to negative p squared. The reason I'm bringing negative here is that whatever number you square it, when you get positive, you multiply by what? Negative. Is that okay? And that gives you something less than 0. So here too, we are going to do the substitution. We know that this thing is x prime prime minus lambda x equals 0. So x prime prime minus lambda, which is okay. So we have, if I put this one, I'm going to have positive p squared x equals 0. So here will be r squared plus p squared equals 0. R squared equals negative p squared plus or minus will be here. So I'm going to have r equals plus or minus p. So the solution for this one too, but remember, because of the negative, you bring I here. So this one is going to give you this is a complex. So for the complex, that I explained it in the other video. That one is going to give you this. Let's say A cos px minus B sine px. So this is how this one is going to give it to you. Is that okay? Please, this side will be plus. Okay, here will be plus. Now after getting this one, let's do the substitution. X is 0. If I put 0 here, I put 0 here. Sine p0 will be 0. So that makes b goes to 0. Cos p0 will be 1. So it means that my a will be equals to 0 because the capital X is 0. So this is what you get. Let's look at the pi. Capital X is 0. So I'm going to have 0 equals a. Even already a is 0. So here will be 0. So everything goes to 0 here. B sine p pi. Because a is 0. You see, we had a to be 0. So if you multiply through it, everything goes to 0. So you don't need to bring it again. B is b. Then x is pi. So this is what you get. Now for this one too, you know that sine p pi is always 0. Because sine 2, if p is 1, sine 2 pi is 0. Sine 1 pi is 0. Sine 3 pi is 0. Sine 47 pi is 0. But b can also be equal to 0. But here, because if you say b should be 0, then you get trivial solution again. So what you do here is that you say that b should not be equals to 0, but sine p pi should be equals to 0. Is that okay? Now after getting this, let's say that let's p pi to be equal to n pi. I've told you that's what we do always. You let p pi to be equal to what? N pi. Is that okay? So even if this place was, let's say, instead of pi, it is, let's say, 2. You say that let 2p equals n pi. After that, you make p the subject. So here, if you make p the subject, you get our p to be equals to n. Is that okay? So what you are going to do is that you are going to substitute this one back to this place so that I have this equals a is already 0, so the cos will go to 0. Because there is n there, let me just bring subscript n. So b subscript n sine. Now our p is n now, so n x. Is that okay? Now you say that where n equals 1, 2, 3 to infinity, we are using n because we want to get to a certain tangent. Is that okay? So we should comply with it. Now after getting this is for x, this one, so we need to find the t. The t was given as t prime minus 17 t, or is 17 lambda t, right, equals 0. Is that okay? So this is what you have. But here, when you get to the t side, you don't need to follow all the procedures. The only thing you need to follow or to pick is the third condition or the third case where you say that lambda is less than 0. So you know that you say that let lambda to be equal to negative p squared. So when I put this one, I'm going to have t prime. Since it's negative, I'm going to have positive 17 p squared t equals 0. So let me clean here. So I'm going to have, you see, this is first order, so it's easy to solve. I'm having t prime equals negative 17p squared t. So t prime over t will be equal negative 17p squared, which you integrate with respect to t. I'm going to have ln t equals negative 17p squared t plus ln, let's say, c. So if I bring that here, I'm going to have ln t minus ln c equals negative 17p squared t. So my ln t over c was negative 17p squared t. You take e on both sides. That gives you t equals c e negative 17p squared t. Is that okay? But because this here, the first solution, we change the p to n, we just replace this p by n. Simple like that. So you say that p should be equal to what? N. Where n is 1 to infinity. So we can say that t subscript n equals c subscript n e to the power negative 17 n squared t. So this is the function for our t, and our x is this one. So we are going to combine these two at this place. You see that we have it here, x and t, so you just multiply them. So let's combine them. You have u in terms of x t equals x at x, t at t. So my u will be equals to my x is bn. Okay, let me bring the t first. T is cn e to the power negative 17 n squared t. Then this one is bn sine nx. So this is what you're going to get. Now this cn, the bn, cn, bn, let's represent, they are all constants, so let's represent it by an. Is that okay? So I'm going to have u equals an e to the power negative 17 n squared t sine nx. Now you could see that this one, we said that the n is from 1, 2, 3 to infinity. So you can sum this one and write it as u equals summation as n start from 1 to infinity, right? an e to the power negative 17 n squared t sine nx. Is that okay? But this one depicts Fourier sine. So we need to find an, then you come and put it there, then we get a particular solution. So now, how do you do that? Before you start with that one, we need to substitute the initial condition that was given. So this is the initial condition, right? It was stated initial condition. This was the boundary condition. We have used it. So the initial condition means that this u is equals to 0, and it is bounded between 0 to what? Pi over 2. So first, let's do that. What it means is that my u is 0, my t is 0, my x is x. Is that okay? So I'm going to have 0 equals summation n equals 1 to infinity an. T is 0. So here will be 0. So everything here will go to 1, leaving sine nx. Is that okay? This is what you have. This one means that my function f at x will be equal to 0. I told you that at that time. Okay. Then let's also look at the other side. Let's look at this. This is one way. Then this is another one. So that one too. My u is 2. So I'm going to have 2 equals summation n equals 1 to infinity. By t is still 0. So everything here will go to 1, leaving an sine nx. And I'm saying that here f at x will be equals to 2 because it's equals to 2. Okay. So if you are going to solve these two, then that becomes our final answer. Whatever we get for a and you come and substitute it here. So let's start with the first one. So the first one, we are going to have an equals integral. Okay, that Fourier sine is 2 over L. But here our L is, you see, it's starting from 0 to pi t. So our L will be pi over 2. But you see, these 2 goes to multiply. But let me maintain. So 0 to pi over 2. The function is f at x is 0. So it will be 0 multiplied by sine n x L over L. Sorry, pi over L, like this. But remember, our L is pi on 2. So if it is pi on 2, if I put pi here, it will be pi over 2. These two will come and multiply and this pi will cancel this. So here will be 2nx. It will be like this. Now, and this is dx. 0 multiply this, everything will go to 0. So I have an equals. And 0 multiply this, everything will go to 0. 0 pi on 2. Is that okay? 0 dx. And this will be 0. If you integrate 0, you get 0. You know, this is definite integral, so you don't have to bring any constant. So this will definitely give you what? 0. So it means that here we don't have any an for the first condition or the interval. Let's move to the next interval. That one we have this one. That one we have our an to be equals to. I've told you that this one could be 4 over pi, or that's 2 over L. So that gives 4 over pi. Integral of the function f at x is 2, 0 to pi on 2. Then sine 2nx dx. You know why it's 2nx? I have explained it here. Now we are going to integrate this one using I think this one you can integrate it straight. If I multiply this one by this, I have an equals h over pi. If I integrate this, this will give us negative cos 2nx divided by 2n, right? 0 to pi on 2. Since when you integrate it, this is what you are going to get. Now let's substitute. If I come and put pi on 2 here, I'm going to have, already these 2 will go into this 4. So at the end, I'm having 8n equals 4 over pi negative cos 2n multiplied by pi on 2. So you see this will cancel this, right? All over n. See, there's minus here, so another minus, so that becomes plus. If I put 0 here, it should be cos 0. Cos 0 is 1, so it should be 1 over n. You have something like this. So my an equals 4 over pi. Now because this one will just give us n pi, that will give us negative 1 to the power n plus 1 all divided by n. Something like this. Let me clean this side again because I'll be using this. So at the end, my an will be equals to 4 brackets open 1 minus negative 1 to the power n, you close brackets, all divided by pi n. So this is what you are going to get. And then, so you come back to this place and you substitute. So finally, our u will be equals to summation n equals 1 to infinity. Our an is now 4 bracket open 1 minus negative 1 to the power n, all divided by pi n. Now, all divided by pi n. Now, before you bring e to the power negative 7n squared t, then sine nx. Sine nx. So this becomes our final answer to the solution. This one. Is that okay? Thank you very much for watching.